last Tuesday we were talking about linear reachability, or reachability for linear systems, and we left off where we were having this problem where there was we were propagating polytopes through these linear equations, and we saw that every single time step up to some depth, we were accumulating this number of vertices, and we had this exponential growth in the number of vertices, and so we were worried because that can quickly become computationally intractable. And so we said one thing that we could do to help with this was represent things as zonotopes. And for zonotopes, the number of generators grows linearly with the depth, and so that was much better. But zonotopes, we can't represent all polytopes as zonotopes, so sometimes maybe that's not what we want to do. And so another option we were talking about at the end of lecture was to over-approximate things. And basically we said an over-approximation is just a set, so here's the set maybe that we want to over-approximate. An over-approximation is just a set that is guaranteed to contain the set that we were trying to over-approximate. And we typically represent these over-approximate sets by putting a bar on top of them. And the idea was that if we have a set that has lots and lots of vertices, then we could over-approximate it with a set that has fewer vertices, and then we have fewer vertices to keep track of. But then we have to make sure that we still want to get guarantees out of this because we're using formal methods here. We want to guarantee that a system is safe. And so we had to say, what kind of guarantees can we get if we only know, for example, the over-approximate set? So say this was our over-approximation of the reachable set. And we said if the over-approximation still doesn't intersect with the avoid set, then we know for a fact that our true reachable set also won't intersect with the avoid set, and so we can still make conclusions about safety even if we over-approximate things. But if the over-approximate set does intersect with the avoid set, then we definitely can't say that it's safe. But we also can't say that it's unsafe because we don't really know what the true reachable set looks like. It could just be like some small portion of this that actually doesn't intersect with the avoid set, but we don't know that. And so we basically just have to leave this as inconclusive. So to recap, if the over-approximate reachable set does not intersect with the avoid set, we can still make claims about safety, we're good to go. But if it does intersect, then we can't really conclude anything. Okay. And so then we left off talking about how, in practice, what we might do to then reduce this computational cost about this growing number of vertices is every once in a while, so every few iterations, this is problem dependent, you could over-approximate your reachable set and then over-approximate it with a set that has fewer vertices and use that from there on out, and so your number of vertices doesn't grow as quickly. And the amazing thing is our favorite package, lazy sets, can just do this automatically for us. So basically all that's going on in this algorithm here is we have some frequency, which is like after how many steps or every how many steps do we want to do this over-approximation. And then we just call this over-approximate function that's provided by lazy sets, give it some error tolerance, and it will over-approximate the set for us with a set that has fewer vertices. And if you want to know exactly how this algorithm works, we do talk about it in the book. And so if you want to know what lazy sets is actually doing when you call that function, you can check out this section in the book. I'm not really going to go through how it works, but after I show you this figure, I am going to show you a little bit of the general concepts behind that algorithm. But first, let's look at this. So this is just visually showing what we were doing where we were over-approximating every few steps. So let's say we wanted to over-approximate the set every 3 steps in our reachability. Then we start with our initial set like we've been doing. We get the reachable set at time step 2. And then when we get to time step 3, we compute the reachable set. This has some number of vertices in it, some number more than 4. And then we over-approximate it with a set that has 4 vertices. And we can control how much over-approximation error we have if we allow for more vertices of this over-approximate set. But let's say we just wanted 4, that's all we could keep track of. And then we take this new set and we propagate this forward from there on out. And so you can see there's a trade-off here because we're getting this extra over-approximation error because we started with this over-approximate set to compute the reachable set at time step 4. So there's this trade-off that goes on between how much computation you have to do and the accuracy of your reachable sets, or the conservativeness of them. So now I want to talk about kind of the general idea for how we can go about over-approximating a set. And the key concept here that's really behind all of this is this idea of something called a support vector. So a support vector mathematically looks like this. A support vector, so this is kind of confusing, or at least confused me at some point. What's interesting about it is it's a function that takes in a direction. So we take in a direction, so this is like a multi-dimensional vector, like that gives us a direction in our space, and it returns a vector. So essentially what this sigma of d represents is this is going to give us the support vector in the direction d. So these are all with respect to some direction in our space. And then what we're doing is we're just looking at all of the points in our set and finding the point that maximizes this like dot product here. So I think it's a lot easier to look at support vectors visually because they're actually like a pretty intuitive idea. And the idea is just like we specify some direction. So let's say we picked this direction here. And we want to find the support vector in this direction for this particular shape, which is a polytope here. And basically what you can imagine for the support vector is all we do is we draw a line that is perpendicular to this vector. And then you can imagine we're just going to take this vector and we're going to push on this line until it's just barely touching the set. So we're kind of maximizing the this dot product here by pushing it as far as we can until we're no longer in the set. So that's kind of what's going on there. And then this point here where this line touches, that's our support vector. So if we were to draw a line to that point, that would be the support vector. And what's cool about this is this actually defines a half space because we know that since this maximized it, all the points below it must be in the set. So this allows us to basically bound the set with some half space, and we can say that everything in this set is going to be within that half space. So this gives us basically a bounding half space. And so then you can imagine like this is one direction that we evaluated the support vector, but let's try to do it in another direction. So let's say that we pick this direction here, for example. So we draw our line, and again we're going to imagine that we're going to take this direction and we're going to push this line until it just barely touches our set. So we do this again, and now this is going to give us another half space. And we know that our set must be, on this side of this particular half space. And so now, no, we don't have a bounding half space anymore, we now have a bounding polyhedron. And then let's do this one more time. Let's pick a direction like this here. So we're going to go straight down, and again we're going to imagine pushing this line down until it just barely touches the set. And now we add in our half space now, and then we have kind of this triangle here, and we've got a bounded set that over approximates our current set. So we have a bounding polytope, which is kind of what we were after. And you can imagine that, so we just did 3 directions here, but we could keep doing this in many different directions, and we'll get different planes and different slices here. And so our over approximation is just going to get more and more accurate. It's going to get closer and closer to this actual set, but it will have more vertices. So that's how we kind of get that trade-off there. And specifically, like the directions that we pick for evaluating the support vector, that's going to determine what this bounding polytope looks like. So these 3 directions gave us kind of this triangle here. If we add another direction, maybe going this way, we'll get like another one that slices through here, and we'll have more than 3 vertices, and etc. And basically what that algorithm that Lazy Sets is using, it just kind of has this smart way of actually picking these directions so that it can kind of most efficiently over approximate the set. And so this is kind of something that you can play around with and hint for project 3. If you want to optimize your leaderboard score on the small problem, you might want to be smart about how you pick these directions. If you just want to pass, you can just make it a box. Okay, is there any questions on that? Yeah.
Are there any intuition you can give for what good looks like in these directions?
Yeah, good question. Let's save that. I'm going to show something at the end that will clear that up, I think. Yeah.
So this kind of don't have to computationally have as many things to look at within this bounding box. But then it's better if we're closer to the actual reachability spaces, and we can make more certain guarantees. Okay.
Yep, that's exactly right. So to summarize, like we're trying to over approximate so we don't have to keep track of as many vertices, But the tighter this over approximation is, the more likely we're going to be able to still make like good guarantees. Because if it gets huge and it's just the entire space, then we'll probably intersect with the avoid set and we won't be able to make those guarantees.
Approximation, like other than like the computational cost of it. Because I guess like for this instance, like there's like the around the triangle regions, like you see like we don't have a lot of the original set in there, I guess, or like the edges of the
like over here
corners. Yeah, like is there any benefit to having like kind of like a bounded area around your reachability set?
I suppose if you felt like you had some uncertainty in your system, you could like inflate your reachable set to kind of account for that, but then that would already kind of be accounted for by modeling it in the disturbances. So typically you want the tightest approximation you can with the fewest vertices. Yeah. Yeah.
Only for convex sets, right?
You can bound any set with its support function, even if it's non-convex. It just might not be tight.
But there might be some like points outside the bounding polytope, right? If I pick, I say like certain directions.
Let me see if I can draw this. So let's say we had our actual set was like this. So this part's no longer inside of it. So this is like our set. So this is non-convex, right? If I evaluate the support function, for example, in this direction, I'll get something like this. If I evaluate it in, I don't know, this direction, I'll get something like this. And like we're still actually going to end up bounding that set. Did that clear it up?
But what if it like, it's like weird and its shape is like it has like a protruding shape.
If we had something protruding?
Shape side of thing.
Like
it's
it was
like extended, extending beyond like one of the bounding,
The support function will always bound your set. Yeah. But yeah, we're typically talking about polytopes in this class, but if you have a non-convex shape, the support function will still bound it. It will bound it as a convex shape. Maybe that clears things up. What are you going to say something? Yeah. Okay. Cool. Okay, so that's set propagation techniques, and then the last thing we're going to talk about somewhat briefly is optimization techniques. And so what we just saw is that we could bound our set with support vectors, and for that we like propagated the set through, we got the exact reachable set, and then we bounded that with support vectors. But we could also just like solve for these support vectors directly without doing any set propagation. And specifically to do that, we would look for the solution to this optimization problem, and it will give us the support vector of the reachable set in direction D. So all this is saying, it looks just like what we had before. We've just replaced the X, kind of the generic X we were talking about before, with the states in our reachable set. So we want to basically solve this optimization problem, and that will give us some bounds on a reachable set. So for example, if this is our reachable set at time step D, what we're doing when we evaluate the support function in some direction is just getting some hyperplane to bound our reachable set at that particular time step. Yeah.
Sorry, what is the here?
All I'm saying is like we don't explicitly know RD. So I'm going to show you in a second like an optimization problem where we just calculate this, but we don't actually know what this was. We're only going to calculate the support vector.
Okay. So this equation could be like D is argmax this thing.
Yeah, it could be that.
Yeah.
And that's actually called the support function, which is introduced in the book. I just didn't want to get too many terms in the lecture, but yeah. Okay. All right, so this as itself, we don't actually know how to solve this, but it turns out we can convert this maximization problem to something that we can solve. And so the idea is we keep the same objective. So we're saying the states at time step D, so that's going to be the states in the reachable set at time step D. We want to maximize this direction vector dot product with that state. And then we're going to choose our states at each time step and our disturbances at each time step. But we have some constraints that say like the initial state needs to come from the initial state set. These are things that we have already specified. The disturbance at each time step needs to come from the disturbance set for that particular time step. And then our final constraint is just the dynamics of the system. So it needs to be the case that st+1 is feasible, basically. It needs to be the state that results when we take a step from st using disturbance xt. So it's just kind of saying, like, we can't just pick any old s1 and xt, like, we need this trajectory to be an actual, like, valid trajectory. So just to summarize that, all this is saying is, like, the initial state needs to be part of the initial state set. The disturbances need to be part of their bounded disturbance sets, and then it needs to be a valid trajectory. So this, like, step function here is just that linear step function that we get for the linear systems. And so it turns out this is a linear program. Everything in this is linear, as long as these are polytopes. And so we actually know how to solve these exactly. I'm not going to talk about how to solve them, but if you want to know, maybe take AA228V next quarter. But yeah, so we can actually solve this. Is there any questions on this setup? Yeah.
So for this to be a linear program, I guess we must have convex initial state sets and disturbance sets.
Yeah, it needs to be convex.
So in that case, I'm wondering what is the advantage of this optimization framework versus if we had just started with our convex sets and done our typical set propagation? Is there an advantage to this optimization technique?
The advantage is kind of the same as, like, if you don't want to keep track of all the vertices, you can get an over approximate set, but you could just directly do it without, like, doing any set propagation.
But in terms of computational efficiency, is there an advantage or disadvantage one way or the other?
I don't know if it's easy to claim. I think it might depend on the system and, like, the linear programming solver specifically that you're using. Yeah.
Thanks.
Yeah.
From a practical standpoint, especially for both the linear systems, when you would want to do this is an over approximation.
It is an over approximation. There's one thing I left out of the slides that's in the book. If you just want to know, is there a point where my reachable set intersects with the avoid set? So if you only want to check the property, you don't actually care about computing, like, what the set actually looks like. You just want to say, is there any point, any state that would intersect with my avoid set? You can solve that exactly using an optimization problem. Very similar to this, you just change up the objective to say, like, basically minimize the distance between a point in your reachable set and a point in the avoid set. And if that goes to 0, then you know that there could be a state in your avoid set. You can check out the book. I didn't put it in here. But so that allows you to do it exactly if all you want to do is check that property. Yeah. Yeah.
So in this optimization problem, the variable we're optimizing is S1 for D and X1 for D, right? Mm-hmm. And then what do we assign to D after like the vector D?
This would be like something you have to pick. So in order to get a bounding polytope, you'll have to solve it in a few directions in order to make sure you get, like, enough support vectors to bound it.
Okay, so you because the sentence above says the solution to this optimization problem will give us D, give us the support
The
vector.
support vector
direction.
direction.
Okay, so we just pick some D,
Yeah.
and then we will solve this, and then this will tell us.
It'll tell us, like, that thing we saw before where we had that, like, shape and then we had the support vector. that, like,
What's the
bounded it.
furthest kind of
Yes, that's
how
what
far it goes? Okay, thanks.
Any other questions on this?
This just formalized the kind of process that we went through of, like, finding the first one. Is that just what this process formalized?
Basically, yeah, it's just that we didn't have to do any set propagation to do this. So we could just write our system down like this and evaluate the support vector already without having to, like, propagate sets and then over approximate those. Okay, so let's look at what this looks like in code. So I'm not going to go through this too much, but we used, I think, convex.jl, maybe, in the book, I forget actually, to solve this linear program. And so we just kind of implement this optimization problem in constraints and variables in Julia, and you can then solve this program in code. That's jump. Cool. Jump.jl. And you can check out the algorithm in the book if you want to see more. Okay, so there's been a lot of questions of, like, what are all these directions and, like, what does it look like when we evaluate the support function? So here's one of the last figures in this chapter where we kind of give you some intuition for what's going on with all of these different directions. And so if we solve this optimization problem in these 4 directions, for example, so that's, like, the 4 kind of axis-aligned directions, then we're going to get a bounding box for our reachable set, because we're going to push up as far as we can, we're going to push to the right as far as we can, to the left and down. And then the samples, they don't tell us what the true reachable set is, because that's inexact to just do a bunch of rollouts, but they give us an idea of what the shape should be. So you can see that when we just do a bounding box for each of our time steps, so we just evaluate the support function in these 4 axis-aligned directions, we have kind of a lot of over-approximation error, it seems, because there's a lot of extra space here where it doesn't seem like any of our samples ended up. So then there's other ways that we could go about picking these directions. So maybe we just sample like 10 random directions and then evaluate the support function in those. That gives us these polytopes. You can see maybe our sampling didn't work out so well, or it wasn't so great because we actually had some cases where it even intersected with the avoid set. So maybe we could increase the number of random directions we do. So maybe we do 50 random directions. And in this case, things seem to get a bunch better. But it turns out one of the best things we could do is all we need is 4 different directions. And all we do is we look at our samples. So at each time step, we maybe do some rollouts, get some samples, and that can give us an idea of the shape of the reachable set. And we look at those and we do principal component analysis on those samples. So if you're not familiar with principal component analysis, no worries. It just kind of gives us what are the primary directions that this data is kind of pointing in. And so when we do that, we can understand what directions might be important to kind of close in this data. And so if we just do principal component analysis and use the directions that come out of that, with just 4 support vectors, we can get this really nice, tight approximation of the reachable set. Yeah.
So this is running the entire LP thing on top of each of the set rollouts. So we do set propagation to get each column, and then we do the LP thing to get the box.
You don't need to do any set propagation to run the linear program.
Right, but how do we get each distinct column? Like,
How do you get these? Oh.
no, like R2, R3, R4.
Yeah, so we'd have to run the LP to get this, we'd run the LP to get this, run it to get this, run it to get this.
Okay, good.
Any other questions on this?
Sorry, to clarify, we still compute the definition of RDM with this with set operations. Right?
To compute this like bounding over approximate set, you don't need to do any set operations. You just need to solve this optimization problem with different directions.
Oh, I see what's happening. Okay, cool, thanks.
Yeah.
And then the rollouts are orthogonal to all of this.
The rollouts are gives us an idea of what the reachable set looks like. So actually we use the rollouts to do PCA because we need some samples to understand. But yeah, you don't technically need them, and it can indicate though that something's going wrong if one of your rollouts is outside of your reachable set, because then you've computed something wrong. So it's a good sanity check. Any other questions on this? Yeah.
Why thinking? I'm just wondering.
In the direction of the x-axis, y-axis.
Oh, okay. And then the 10 random, just 10 random directions.
Yeah, these we just sampled random ones, and this one we actually looked at our rollouts and tried to understand what were the best directions we could pick.
Rows.
No, so the number of vertices will be, is it equal to the number of support vectors? Possibly equal to the number of support vectors, I don't think about that. But in general, this has more vertices than this one. This one has 4, these have 4, and this probably has close to 50, and this probably has close to 10. Yeah.
In the code, so the optimization problem is, you said it's linear everything, right? Okay. Good, because you use a solver that's can do much more than linear. But that's why I think it's a kind of an overkill situation. But again, just to clarify, we don't need anything.
Well, Junk has lots of different solvers.
Sure, when you go to the code, and it's not so important, but use SCS optimizer. I was like, what's this? And it's it can do a lot of things, but we just need the linear
You just need the
solve
linear,
version.
yeah. You can plug in any solver you want.
Great. Well, yeah.
Yeah. Okay, cool. So that wraps up this lecture on linear reachability, and we'll go to the next one. Okay.
Maybe just a comment.
Yep.
I have a question earlier from last lecture. Could we actually find the sort of adversarial examples, counter examples? And I guess the LP would actually give us that, possibly, if
That's
or although maybe it's still an over approximation, so maybe even if we get the disturbance sequence, it's not going to.
The one that I was talking about that I didn't put in the slides, where you can solve it exactly just to check if it intersects with the avoid set, that would give you the example. So yeah, good thing in there. Okay, so now that kind of wrapped up reachability for linear systems, and now we're going to talk about reachability for nonlinear systems. Okay, so in this previous lecture, when we were doing all this set propagation stuff, which is what we did for most of the lecture, we saw that we could apply these nice linear operators to polytopes. So specifically, we could apply matrix multiplication and addition to polytopes. But it turns out that if we try to apply nonlinear operators to polytopes, this becomes much less straightforward. So things are generally a little bit more difficult for nonlinear reachability, and I'll demonstrate kind of why, or what this looks like anyway. So let's say we want to apply a linear operation to some polytope. So in this case, our polytope is just has two vertices. It's just a line, or a line segment. We apply some linear operation to it, so maybe like 2x plus 1, so this is just multiplication and addition like before, and the line turns into something like this, which is still a polytope, still a line segment. But now let's imagine that we have the same polytope or line segment, and we apply some nonlinear operation to it, so maybe we take the sine of x plus 1 or something like that, and then we get this set out. That's definitely not a polytope anymore. And in fact, it's not even convex, because we're able to take 2 points in this and draw a line between them, and the line does not lie in the set, and so this is non-convex. As we kind of mentioned last lecture, non-convex sets are much more difficult to work with. It's a lot less straightforward how to do these kind of operations on them, and while it's possible, there's lots of research on this, it's not so easy. So that's kind of what increases the difficulty for this nonlinear reachability. Okay, but one thing that we can do, and that we're pretty much going to do for the rest of this lecture, is we can take these things that are not polytopes and bound them or over-approximate them with things that are polytopes, so make them easier for us to work with. So that's kind of going to be the general idea behind like all the topics that I talk about in lecture today. So the first one is interval arithmetic. The second one extends that to something called inclusion functions. Talk about something called Taylor models, concrete reachability, and partitioning. Okay, well, let's just get into it. So, like I said, we just saw that we can't really propagate arbitrary polytopes through nonlinear systems. But it turns out one thing that we can do is actually propagate these things called intervals. So an interval is probably kind of exactly what you think it is. So we represent intervals like this, where we have some variable x, and we put these 2 brackets on it. That means that that's an interval over the variable x. The interval is defined by some lower bound, which we represent with this like underline x, and some upper bound, which we represent with this overline x. And the interval is just all x that are between the lower bound and the upper bound. So nothing too crazy going on. It's kind of exactly what you would think. We start at some lower bound, go to some upper bound, and the interval includes all points in between it. We can go beyond just 1D though. So when we do that, we end up with this thing that we call an interval box. And to do that, we just take the Cartesian product. So this here is the Cartesian product of a bunch of one-dimensional intervals. And we represent that by same thing with these brackets here, but x is now bold-faced because it's a vector. It's more than one dimension. So just to see what that looks like, you can imagine we just take 2 1D intervals, so x1 and x2. We just kind of take their Cartesian product, which just looks like kind of rolling them out and looking at where they overlap. So the Cartesian product of x1 and x2 is this like bold x, this square here. This might look familiar, hopefully it looks familiar to all of you. It's just the same thing as a hyperrectangle. So when people talk about interval arithmetic and intervals and stuff, they often call them interval boxes, but it's the same thing. It's a hyperrectangle. It's like axis aligned, this kind of axis aligned shape, axis aligned polytope here. Okay, so that's intervals and interval boxes. And the idea here is that instead of doing, the simple arithmetic operations that you all learned in elementary school on single points, we're going to now extend them all to do them on intervals. Okay, so let's, for example, add 2 intervals together. So here we have this interval x, it goes between -1 and 1. We have this interval y, it goes between 2 and 4. And we need to define what it means to say that we add 2 intervals. And to define that, we're just going to say that the interval x plus the interval y is going to be all points x plus y, where x came from x and y came from y. So this is very similar to like what we were doing with the Minkowski sum. We just take all the points in these two sets and we say like the new set is any sum that we could get from any combination of those points. So looks very similar to what we were doing with the Minkowski sum. We take 2 points in these intervals, add them together, and we get different points that are in this kind of resulting interval. And if we could do that with all infinite combinations of points, then we would get the interval x plus y. So we have a lower bound and an upper bound here. And it turns out, we don't have to do all infinite points just like before. And just by looking at this, can anyone guess what the lower bound and the upper bound for this interval would be? Yeah, 1 to 5, yeah. So basically what we did is we just add the lower bounds for these two. That's kind of the lowest value that we're possibly going to get. So we get 1, and we add the upper bounds, 1 and 4, and we get 5 up here. So yeah, nothing too crazy going on here. But what's cool is that, so we can write down like a general form equation for this. So the interval x plus the interval y is just going to be the sum, the lower bound will be the sum of their lower bounds, and the upper bound will be the sum of their upper bounds. And this operation is known as the interval counterpart of addition. So that's what people call this. So like, we have regular addition on like single points, and then the interval counterpart is this function here. And it turns out we can define interval counterparts for all of the, wonderful arithmetic operations that you know and love from elementary school. And so we could do it for addition, subtraction, multiplication, and division. So this is just defining what that means, where this little dot here you can just, replace with your favorite of these operators. So for example, if we wanted to do like multiplication, then that would mean that the interval x times the interval y is all points x times y, where x came from x and y came from y. So again, just doing all of these different combinations. And so we can actually write out in kind of closed form what all of this would look like. So for subtraction, it's very similar, but instead of adding the 2 lower bounds, we subtract the upper bound of y from the lower bound of x, and do kind of the opposite to get the upper bound. For multiplication and division, it's like slightly less straightforward. You need to basically test out all combinations of the endpoints when you multiply and divide them to see which one makes the min and the max. But that's really all that's going on there. So basically what I want you to take away here is like, this is basically asking to be like coded up, right? Like you're sitting here like, oh, I'm just going to write all these wonderful functions that take all of our normal functions and just operate on intervals instead. And so that's kind of the idea. And then it turns out it's also possible to define these interval counterparts for other elementary functions. So not just like plus, minus, multiply, and divide. We can take some other, like any arbitrary function or elementary function, input an interval, and then the interval counterpart is just kind of the tightest interval that fits all of the points when we apply the function f to points in the interval x. Yeah.
Can you go back one slide? So you have the division there. I feel like this cannot possibly be if y is like from negative to positive, then somewhere in the middle you divide almost by 0, you get some infinitely large value.
You would divide by 0, so this is not defined.
Or divide by like...
If y contains 0, this is not defined.
Sure, but also y is goes from negative to positive.
That would mean it contains 0.
It goes 0. Yeah. That's true.
Yes. Okay. So the interval counterpart is just all of the, if we evaluated f on all of the points in x, what is kind of the tightest interval that would contain all of those resulting points. So to see what that looks like, let's take this function x of x. So it looks like this. And let's say that we wanted to evaluate it over this interval from 1 to 2. So what we could do is we could just take the function value at 1 and the function value at 2, and then the interval is just going to be all values between those two function values. So this is the result if you apply x to this interval x. Okay, so this is basically the interval, and you can see it contains all points that the function outputs within that range, and it's a tight interval. And in general, you might be thinking, okay, like all I then really need to do for these monotonically increasing functions like exp, and there's other ones that we might be interested in, like log, square root, all we need to do is take evaluate the function at the lower bound of the interval and evaluate the function at the upper bound, and that will give us the interval counterpart for that function. Yeah.
I'm just curious for this. In the 1D, we have an exact bound. If we have multiple dimensions for x, do we still have exact bounds, or do we have some sort of over approximation at this point?
We're only talking about like 1D functions right now. Okay. So yeah, we can still define interval counterparts for non-monotonically increasing or decreasing functions. We just might have to kind of consider multiple cases. So for example, let's say we wanted to define the interval counterpart for the function x squared. Then, if let's say we were going to evaluate it over this interval here, and we had, so it's like minus 1.5 to 1, and we look at the two function values. If we just included everything between these two function values, we'd be missing all of this stuff down here. So we just need to make sure that we check for that case when we evaluate this function here. So basically we say, if 0 is not in the interval, so then that means we're on this side or we're on this side, then we can just kind of check the endpoints of the interval and figure out, which one's bigger. But otherwise, if 0 is in the interval, then we are going to need to include this kind of minimum at 0 here, and then we're going to look at these 2 points. So we're in this case here. We're going to look at these 2 endpoints, see which one's higher, and then everything in the interval will be between 0 and that endpoint. Okay, so it might seem like kind of a lot to keep track of in your mind, but I just want you, you can go back and study this later, and I think you'll agree with me that this is the right thing to do to define this, even if you don't see it immediately. But I just want you to realize that for most of these elementary functions, like square and sine and exp and whatnot, we can actually go and implement, think about it and just write down this rule, and then we could just code it up and we can now pass intervals through functions. So that's kind of the idea I want you to take away. So here's just an example of a few of them. We did exp, we did x squared. Here's a similar idea for sine of x. We can do this for many elementary functions. And no worries, you don't actually have to go sit down and code it up because someone's already done that for you. And there's a package called intervalarithmetic.jl in Julia that's quite good. You can just take all the native Julia functions like sine and exp, and you can go ahead and pass intervals through them, and it will keep track of all these things for you, which is pretty cool. Okay. But so we just talked about passing intervals through a bunch of nonlinear functions and weird stuff here, but let's get back to what our goal is here. So just like in the previous lecture, we want to compute the reachable set at some depth d, and we define that as all of the states at depth d that we could reach given our rollout function if we start in some initial state set and have these bounded disturbance sets. And so in the previous lecture, this reach function was really nice and linear. So we could just, apply this linear equation over and over again, and we just keep getting linear functions of our state and disturbances. And so we didn't have any issues passing sets through them. But now, in many real world systems, this function is actually nonlinear, and we can't just get away with doing these linear set operations. So for example, the inverted pendulum that we've been using so much throughout this course, that's a nonlinear system. So these are actually what the equations look like for the next state for one time step for the inverted pendulum. So theta is actually a linear function, but then to get the next velocity, there's this sign in there. So that makes it nonlinear. And then you can imagine to do the reach function, we have to do a rollout up to depth d. So we're going to apply this equation kind of over and over again. So things are going to start getting multiplied by each other. So we don't just have this one sign. We have many iterations of this sign all kind of getting multiplied together. So this function is kind of highly nonlinear after a few time steps. And this function is a little bit more complex than the elementary functions that we were using for interval arithmetic. So, in our interval arithmetic, we just had one sign. We didn't have any addition, with that or anything like that. We just had one sign, or we had two things added together, but this is a whole equation here. And so our interval arithmetic doesn't kind of just directly apply to these more complex functions. And instead, we need to use something called an inclusion function. And so yeah, kind of the best we can do is this thing called an inclusion function. And what it is just an interval that's guaranteed to contain the interval from the interval counterpart. So basically the idea is the interval counterpart is exact. It's the tightest interval we can get on the output of the function. But that's not always possible for us to compute as these functions get more complex. So we can typically compute it for those elementary functions like sine and x that I was showing earlier. But when we have, combinations of those functions or like a bunch of them multiplied together, we can't always just compute that interval counterpart. But what we can do a lot of times is compute something called an inclusion function, which is just guaranteed to contain the interval counterpart. So it's kind of the same exact idea as an over-approximation, where this is the interval counterpart here, and we're just saying this interval counterpart is guaranteed to be a subset of the inclusion function. And we differentiate between an inclusion function and the interval counterpart by putting these brackets around the f for the inclusion function.
Sorry, can you just say again why we can't directly as a brackets, like kind of interval?
When you have these like more complex functions, it's just not obvious how to define the interval counterpart for them.
I see. So when we are having a monotone function, we should be not doing this. We should be just using functions. Right?
If you know that your function is monotonic, you should just use the endpoints.
Okay, great.
And then you can't define an interval counterpart. It's just most of the time we can't do that.
Makes sense.
Yeah.
To follow up on that question, so I understand that our dynamics for the inverted pendulum is more complex, but it seems to be composed of these sort of sub-functions that we do know how to compute intervals for. So I'm wondering why can't we, compute those individual intervals, and then now we, for example, adding them, we can do that as well. So I still don't see why we can't, compute the exact interval.
Yeah, great question. You can do that. That's actually the first thing we're going to talk about with inclusion functions. It turns out it doesn't give you the interval counterpart if you do that. Yeah, which I find kind of not what I would have thought, but it's true. Okay, so let's keep going here. So again, this is the interval counterpart, and then this is the inclusion function. And a lot of times all we're able to calculate is this inclusion function, and we're not able to actually find the interval counterpart. And just to look at this visually, so let's say that this is the interval counterpart. A lot of times we don't know it. And then the inclusion function is just going to give us some interval that's bigger than the interval counterpart, or contains the interval counterpart. So you can think of it just like what we were talking about before when we were talking about over-approximations. It gives us an over-approximate interval for the function. Okay, so let's think about this for a second in the context of reachability. So for reachability, we want to basically pass intervals through this reach function to find an interval over the state at depth d. And all I'm going to do for this chapter, we just renamed the reach function to be r because we didn't want to write reach a bunch of times. So all I did was rename this function. Nothing else happened here. But then what I'm going to do is I'm going to break this function up into a set of functions that take in, so right now this is a multivariate function. So it takes in x and x, s and x, which have multiple dimensions, and then it outputs a state, which also might have multiple dimensions, because our states are typically, could be like two-dimensional or whatever. And what we want for these interval arithmetic, or these inclusion functions that we're generating, is we want a function that takes in, it can take in states that are multivariable, or sorry, not multivariable, multidimensional, but we want it to output a single variable. So all I'm doing is just rewriting this as a set of functions that output a single variable. So R1 will output the value of the first state variable at time step d, and Rn will output the value of the nth state variable at time step d. So all I did was kind of break it up and stack them all on top of each other. And just to make that concrete, what this would mean is the inverted pendulum has two state variables. It has theta and omega, the angle and the angular velocity. And so R1 is just going to output the value of theta at depth d, and R2 would just output the value of omega at depth d. So that's all we did, was just break it up. But if we do it like this, then what we could do is define these kind of inclusion functions for each of those reachability functions, so for R1 through Rn, and that's going to get an over-approximate hyperrectangular reachable set, because we're going to get an interval over the possible values for every single state variable, and then when we take the Cartesian product of those, we're going to get an interval box or a hyperrectangle, and that will give us an over-approximate hyperrectangular reachable set. What questions do you have on that? I think I have one more thing. Okay, so if you do have questions and you're too afraid to ask or don't even know what to ask, no worries. The TLDR here is just we're just trying to pass intervals through a system. So we're taking our rollout function, and instead of passing a state and a specific set of disturbances, we're passing an interval over our state and over our disturbances and trying to get an interval over the states that come out.
How do we get the initial intervals to put into R?
You would define them in the same way that you define like the initial set and the disturbances. So you might have to over-approximate them into intervals. But.
And sorry if you said this, I just missed it. How did you get the inclusion functions for R?
Oh, we're going to talk about that.
Oh.
Yeah. So this is just assuming if you could find these inclusion functions, this would give us an over-approximate hyperrectangular reachable set. And we're going to spend like pretty much the rest of the lecture talking about how to actually find them.
Okay, that makes sense.
Yeah.
So, I guess like, since this is a non-linear system, we're using these intervals now to kind of define this. So then, are the only shapes that we can get from this, as we go up into these larger dimensions, can they only be of the shape of like a rectangle form now? Like, we don't have all these different
Yes.
types.
Yeah, that's exactly right. We can only get hyperrectangles out anyway.
So there's no way to like optimize that further. I guess it's always going to be of that kind of shape.
It's always going to be of that kind of shape. So that's kind of one drawback of this interval thing. So we kind of have to make some sacrifices when we go to this nonlinear world. And so one thing we can do is say we're going to do everything intervals and we're going to accept the fact that everything's going to be hyperrectangle. And of course, like if our reachable set, isn't hyperrectangular, like if it looks something like that, and we have to bound it with our hyperrectangle, it's kind of a bummer because we're getting all this extra like over-approximation error, but we're just going to have to kind of accept that.
I guess like similar to the previous, like one of the examples with PCA, principal component analysis, can you do that, but in this case? Or like
not using interval. You might be able to do interval arithmetic on a transformed version of the system and do that, but yeah, not super straightforward how to do that. Yeah. Okay, so let's talk about how to get these inclusion functions. So there's a few different ways, and we're going to go through them. The first one is the natural inclusion function, which is basically what you already suggested. So let's look at an example of what this is. So let's say we have some function now that's x minus sine of x. So this is, not just one elementary function. We define an interval counterpart for this and an interval counterpart for subtraction, but we don't have one for like all of x minus sine of x. But you might say, well, okay, let's just like plug in the interval counterpart, which is kind of what you were suggesting there. And if you do that, you get something called the natural inclusion function. So all you do is you plug in the interval for x in all of these. We know how to do sine of an interval. That was in our interval counterpart. We know that. We know how to do we know how to do subtraction then between two intervals after we evaluate that, and so we know how to evaluate this function, and it's called the natural inclusion function. But let me show you, okay, so the gist there is that you just replace every elementary function in this function with its interval counterpart. But it turns out, maybe somewhat surprisingly, if you do this, you actually get kind of a huge amount of over-approximation. So what we did here is we have this function, and we input the interval between -1 and 1. And then this is the interval that we got out. So we said we're guaranteed that the function values between -1 and 1 will end up in this purple space. But really, if we look at so again, if we knew this was monotonic, we could just take these endpoints and we'd know the actual interval, but we're saying we maybe don't know that. So the actual, interval for the function values that we'd get between -1 and 1 is much smaller. It's like this space in the middle here. And so all of this stuff that we got out here is over approximation. So it might not be super obvious that that's what happens, but it turns out when you use the natural inclusion function, it tends to be overly conservative. And the reason for this is something called the dependency effect. If you want to know a lot about it, I would recommend checking out example 8.2 in the book. But the kind of gist of the idea, I think it takes some time to kind of digest, which is why I'm not going through it super detailed in lecture. You can check out this example. But the idea is when we plug x into this function, we're always plugging the same value in for x in both of these spots. But when we switch out to intervals now, we're kind of saying that anything in this interval could get subtracted with the sign of anything else in the interval. So they're not always the same value. That's kind of the idea behind the dependency effect. If you want to know more about it, though, I would definitely recommend checking out that example. If you don't want to know more about it, you can just be like, okay, natural inclusion functions are bad, and move on with your life. That's also fine. Okay, so this is how we implement the natural inclusion function. So this part here is just implementing that R. So we're taking a rollout of our system and grabbing the last state at depth D. And then we just go through at every single step that we want to compute it for, get the intervals for the initial state and the disturbances for that point, and then just pass those intervals through our rollout. And so, yeah, what's super cool is like in Julia, we can just pass all these intervals through our rollout code, no problem, everything works. Here's another ad for Julia. Okay, so let's see this in action. Okay, so here's our inverted pendulum system. We're going to start in this kind of set of initial states where we have some bound on what thetas we could start out with and some bound on the initial velocity. So here's the first time step. Let's go to the second time step. Okay, so now it's actually already off the thing. I told you natural inclusion function is not so great. And so these samples, again, we don't know exactly what the reachable set is, but it's probably shaped something like these samples that we got here. And so we're way overbounding this reachable set. And if we go further, yeah, we're kind of done now. So now we have to conclude, well, inconclusive, we don't know if it's safe or not because this is over approximate. Based on our samples, it looks like it's safe, but we can't say that for sure. And we've kind of lost all ability to draw like conclusions from our analysis now. So yeah, there's the natural inclusion function. So I know that all of you are probably wondering now, like, wow, there must be a way to do better. Of course there is, we wouldn't just stop there. Okay, so yes, can we do better than this? Yep, just got to bring back a theorem from calculus. Okay, and that theorem is specifically the mean value theorem. I don't know about you guys, but when I learned this in high school, I was just like, why on earth does this theorem exist? Like, I'm never, ever going to use this in my life. And then I sat down to write this textbook, and here it is. So all of you can go back and thank your calculus teachers now and just be like, I'm sorry, that wasn't pointless. I didn't know any better. So here's the mean value theorem in case you've forgotten it over the years. So for a function that is continuous and differentiable, that part is important. You need to make sure your rollouts are always continuous and differentiable if you want to do this. On this interval over x, there exists a point in that interval such that this fact is true. And what this fact is saying is the slope of the secant line between the endpoints of the function on that interval is equal to the slope of the tangent line somewhere in that interval. So I think it's easier to kind of visualize what this theorem is. So we have this kind of lower bound on x and upper bound on x. This is our interval that we're interested in. Here's our function. And basically we can look at what are the function values for that, the endpoints of the interval. And then this part here is the secant line. So we take the difference between these function values divided by the difference here. So that's this slope here. And then we know that at some point inside of this interval, there must exist a point where the slope of the tangent line at that point is equal to this slope of the secant line. So yeah, I mean, I don't know. I learned this in calculus and I was like, okay, cool. Like, I don't know. I thought this was quite silly, but we're gonna use it now. And I don't know, I found this online the other day, so here you go. If you have trouble remembering the mean value theorem, you can draw some eyes on it. And if you flip it upside down, everything is still valid, but I guess now you could call it the nice value theorem if you so please. Okay. So that's the mean value theorem. Okay, now I'm gonna make some extension to it. And this is going to seem like a little bit weird at first, like it's going to seem like it's going nowhere, but I promise it is going somewhere, and yeah, just bear with me. So we're going to now take the center point of this interval, and we're going to pick some value x in the interval. So we can pick any value x, we're going to pick this one. And now we're going to apply the mean value theorem to the interval between x and c. So we're going to say, okay, let's connect these two, get the secant line, and then somewhere in here, there must be a point where the slope of the tangent line is equal to the slope of the secant line, and we'll call that point x prime again. Okay, and so x prime, we now know where this thing happens, is in the interval between x and c. And now I'm going to do something weird, and I'm just going to be like, x prime then is also in the interval of the original interval over x we had, so the lower bound and the upper bound. So this is kind of silly. We just said, like, we took this smaller interval, and we're like, we know it's in the smaller interval, and all I'm saying is, like, yep, and we also know that it's then in the, like, larger interval that contained it, which is going to be useful in a second. Okay, so now we can kind of say that this mean value theorem implies that if we take the center point of the interval, then there exists some other point in that interval. So again, x prime is in this, like, bigger interval. We actually even know it's in this smaller one. Such that this is true. So this is just saying the slope of the secant line is equal to the slope of the tangent line in there. And we can do that for, like, any x in this interval. So I could move this x. So for example, I could move this x over here, and this fact will still be true. Okay, so it seems kind of weird. Like, I haven't gotten to the point of why you would do this, but if you agree with me that all of this is true, we can kind of go to the next part. So yeah, are there any, like, questions on how we got there? Yeah. I think it's true even at the very boundary points, yeah. Because yeah, I guess you could just imagine we, like, take this x and put it over here, we're still going to have a value that's in between these two where that happens. We're saying we're going to create a new interval between the center point and just, like, some value x that's, like, within the interval. And then the point where the secant line thing happens is always going to be in the bigger interval. Okay, so then we can take this, and all I'm going to do is take this thing that we know happens and just rearrange it. So all I did was multiply both sides by x minus c, and then added the f of c over to the other side. And then here comes the cool part. So this is now, we know now our function f of x is equal to this at some point in the interval. And so what we can do is we can just create now the natural inclusion function for this function, and we get a natural inclusion function, or in this case now we're going to call it a mean value inclusion function for f. So all I did was take, f of c is just f of a number. It's the function evaluated at the center of the interval. We don't need to do anything there. Here we replaced this x with the interval version of it, and then we also know that x prime is in the interval x, so we can also replace x prime with this interval. That's kind of the key insight, like that's why we did all of this stuff. And then if we just grab the natural inclusion function for this f prime, so natural inclusion function for the derivative of f of x, then we know that all of this holds true. Okay, so we're going to call this the mean value inclusion function. And we can generalize this to more than one dimension. All we do is replace everything with vectors, and then we replace our derivative with the gradient. Okay. So, yeah.
Can you just go back on the last slide?
Yeah. Okay. So I'm going to actually do, like, a kind of worked out example of applying the natural inclusion function versus the mean value inclusion function in order to, like, make this a little bit more concrete. So let's try to do this here. Can I write? No. Okay. So we're going to try to evaluate the natural inclusion function of this function over this interval. So the natural inclusion function means that we just replace everything with their interval counterparts. So we're going to do this. Okay, and so then we're just going to plug in the interval -1 to 1 for this. And I don't expect you to be able to do this in your head, obviously, but if you apply sine, the interval counterpart of sine, to this interval, you end up getting -0.84 to 0.84. And then if you apply the interval counterpart of minus, now it's going to be weird because it looks like an equal sign, but if you apply the interval counterpart of minus to both of these, you end up taking this and subtracting 0.84 from it, so you get -1.84 to 1.84. And that is our final guess for the interval that bounds this function, for the natural inclusion function. Okay, let's try to do it now for the mean value inclusion function. So we need the center of our interval, so that's going to be 0 because we're going -1 to 1. And then we know for the mean value inclusion function, we're going to say that it's equal to f of c plus f of x. Sorry, this should be the gradient. And then of this interval x minus c. Okay, so let's start plugging stuff in. So we've got f of 0, because c is 0, plus, and then the gradient of x minus sine of x is going to be 1 minus cosine of x. So we're going to do cosine of this interval here, times x minus, and then c was 0 again. F of 0 turns out to also be 0, if we plug that into the function up here. So then we have 0 plus 1 minus, and if we do the interval counterpart for cosine, we get 0.54 to 1, and then this is like, we're just subtracting 0, so we get the same exact thing that we had before. Okay, and so then if we kind of keep plugging along, we end up getting do the interval counterpart for multiplication, and we get minus 0.44 comma 0.44. Okay, and so I recommend maybe kind of going back through more slowly at your own pace and trying to do this yourself, and I'll probably make some exercises that drive this home too. But what I want to get across here is like, we're now doing much better. We got like a much tighter interval when we did the mean value inclusion function than when we did the natural inclusion function. So that's pretty cool. Yeah.
Can you elaborate a little bit why this is?
It's pretty much the dependency effect. So if you rewrite it, we're going to talk in a second, kind of compare this to first order approximation. But if you look at this now, like this is kind of a first order approximation of the function. And it actually then kind of undoes the dependency effect in a way.
Why is it that sort of first order approximation gives us less?
I think it's because it makes it linear, but I need to think about that. Because you can kind of...
But like two linear functions, it's still...
If you but you can always simplify linear functions to get rid of the dependency effect, which is kind of interesting. That's what we talk about in that example 8.2, so you can check that out. Yeah, I don't know. I never had a super great intuition for this, to be honest, but yeah. Yeah.
So you said this also works for higher dimensional functions, right?
Yeah.
And I'm just trying to think, before we were in higher dimension constrained by like always getting like boxes because we just take the interval at first d and interval at second d and kind of cross multiply. Does this help us get rid of this kind of square shape or
No, so if you remember, we split the reach function into like one, so every function will output a one-dimensional interval. So then we're going to still have to take the Cartesian product of all of those one-dimensional intervals you're still going to get. Yeah. We are going to get to a point in this lecture, possibly not today, where we talk about ways to not have to do hyperrectangles, but for now. Okay, so yeah, again, you can check this out, kind of go through it a little more slowly, hopefully, on your own time. But just to kind of verify what we just did, here's like kind of graphically what this looks like. So this is all the math that we just did. So if you remember, we got like minus 1.84 to 1.84, so that's what this looks like. And we saw this before, like our natural inclusion function doesn't look so good. Our mean value inclusion function looks much better, which is pretty cool. Okay, but it is possible to actually do even better. So this was called the mean value inclusion function, and I already kind of gave it away, but does this function kind of remind you of another topic that you learned about in calculus? Yeah.
Taylor series?
Yeah, Taylor series. This is actually just a first order Taylor series, or in other words, like a linear approximation of the function. But we don't have to just stick to first order Taylor series, and there's actually, it turns out, a way to generalize this to something that we call Taylor inclusion functions. And for that, we just use, n terms of the Taylor series to do this. So I didn't prove that this works. I just proved it for this first case. But hopefully, in your mind, you could believe me that it's okay to just extend it to more terms of the Taylor series. Okay, and then it turns out that like a zero-order Taylor inclusion function, we're just going to have this first term, and we're going to end up just passing the interval through the first term instead. And that becomes the natural inclusion function. And then a first-order Taylor inclusion function is the same as the mean value inclusion function, because we're just going to have these first two terms. So this is kind of just a more general case of the first two things that I just showed you. So it turns out it really does make a difference, which is pretty cool. So we can go beyond, the natural inclusion function in this first order, which is the mean value inclusion function. Second order doesn't actually help that much, it seemed, for this case, but third order, we got a very tight interval, which is pretty cool. Yeah.
Does this kind of hold for most general functions? So I have reason to think that it would work well here, just because like the derivative of that is very flat.
Yeah.
In that region, and I guess you can see that where we're taking that interval.
Yeah.
So in general, do we still have this kind of?
Yeah, that's a great question. So, and actually this figure kind of shows a little bit what you're asking, because so this first order approximation, when we do like Taylor series, a first order approximation is a linear approximation of the function. So the more linear the function is, the better this approximation is going to be. And so you can see like we get a much better result. In this case, so these are the same case, except I evaluate over a slightly bigger interval. So this interval in here, it's like pretty linear, like it's kind of like almost a line, right? But if we expand this interval out now, such that it contains more of this kind of non-linear part of the function, this doesn't actually work. Like the first order doesn't work as well. So it really depends on kind of how well your Taylor model fits inside of that interval, fits the function.
Oh, we still see like a nice trend though, right? As we increase the interval.
Yeah, I mean here, like it didn't make a huge difference to go to second order, so you don't always know like how much it's gonna help, but yeah. Okay, so here's the code for the Taylor inclusion function, and I'm not gonna really go through this code super in detail, but just to point out, like here, this is basically the mean value inclusion function. So we actually only implemented it for orders of 1 and 2. It's not super straightforward to do for higher orders, but can be done. But so for order 1, where we just have this mean value inclusion function, we evaluate it at the center point. We add on the gradient of this reachability function, which calls our rollout, and we pass the interval through that gradient, and then we multiply it by this interval minus the center. Okay, so this should like hopefully blow your mind, because like we just, like this is what we're doing. We're taking this R function, this calls our rollout function that we've just like arbitrarily implemented in Julia code to like define our system. We're taking the gradient of that, and then we're passing an interval through that gradient. And Julia just allows us to do that. It just allows us to pass an interval through the gradient of the rollout function. Crazy. Like, if you can show me another language that can just do this so seamlessly, like, it's amazing. Like, when we were coding up this chapter, we were like, well, let's just try it. Like, I feel like we can't pass an interval through a gradient, but like, let's just try it. It just works. So, amazing. Multiple dispatch.
How does it differentiate the whole function plus the interval?
Well, the gradient is like implemented in this multiple dispatch type thing, so we can just pass an interval through the thing that's already implemented for the gradient, and it all just works nicely together. It's absolutely amazing. So
Checkmate,
yeah,
Python is
so-
this.
there you go. The other thing I realized when I was making these slides and like blowing up the emojis is I think emojis are really meant to be like small. Because like, I don't know, this is pretty creepy when you like blow up a mind blown emoji. Like I didn't really realize that that's what it looked like. But anyway. Okay, so let's see if this fixed our problem. All right, so now we're going to go a Taylor inclusion function of order 1. Okay, so here's our new bound. So this has gotten better. We had natural inclusion before, not so great. Order 1, looking better. This is good. This is promising, right? Okay, and then order 2 actually for this problem. So like as you're asking, it doesn't make a huge difference. So yeah, I'll just stick with order 2 for now, but it doesn't really make much difference. So this is looking a lot better. Yay, oh darn. Okay, so we almost got there, but not quite. So this is better though. So right, like at these time steps, we were able to say quite a bit more than we could with the natural inclusion. So we are getting better. Why does it get?
The Taylor one. Why does that also like have difficulty like?
Later on? Yeah, that's a great question. So, can anyone guess why, actually? Why is it harder for more time steps? Yeah.
You're stacking on more disturbances, so the final benefit is going to be larger in this case.
Yeah, that's true, but that would actually just make the exact reachable set grow at each time step. But why does it seem like the over-approximation is getting worse?
Maybe we're reaching the non-linear. Maybe we are experiencing more non-linearity.
Yep, that's exactly right. So like as we stack on more time steps, we had that sine function in dynamics. Now we're gonna do that sine function times like a thing that was already had a sine function in it times that, and we're just like kind of compounding these non-linearities. So that's exactly right. So as we kind of go further in the future, and we'll talk about later in the lecture ways to kind of prevent this. As we go further in the future, we kind of compound those non-linearities, and it's still not able to provide a good approximation then. Yeah.
Okay, so is the issue here with kind of like the non-linearities kind of like stack up and over like 4 time steps and just like explodes out?
Yep, that's exactly right. Yep.
Oh, okay.
Because I mean, basically, like the second order Taylor inclusion, it's not a linear approximation anymore, but it's it's not a linear approximation anymore, but it's like a second order approximation. And as you kind of stack up these non-linearities, even a second order approximation is not.
Could you solve that by just adding like a higher order Taylor polynomial, or would you have to
you could add a higher order Taylor polynomial. It might not be as easy to compute.
Intractable if you're computing large time steps, right?
Yeah, it might be difficult. Yeah.
Could you imagine? Just like match. 6 time steps do like 6 degree.
I don't think it like exactly corresponds because like sine is already like non-linear. Like it's not like it's not like just one is gonna like fix it all. Yeah.
It's probably true mod Taylor convergence. So you like take the Taylor series. Say your function is analytic. You take the Taylor series of your thing that you're trying to approximate. The rate of that convergence is probably linear with respect to timestamps in your estimation, right? Because you're just multiplying a bunch of polynomials.
I don't know, because you're multiplying. I don't have to think about it. But yeah, these are all really good observations though in terms of like, I think it's really good to have these intuitions of like, what should work, what would make things better if things are like, too over approximate. Okay, let's see, what do we have next? Let's go back here. Okay, so that kind of wraps up Taylor inclusion functions, and I think in the last 2 minutes, I'm just going to get you excited about coming back next week. So we just talked about these inclusion functions, and a lot of you, were like, man, we're just only ever going to get these hyperrectangles. Like, that's really bothering me. Bothers me too. And it's like, no matter how high the order that we go up, like, we're still always going to get these hyperrectangles. So if you want to not get hyperrectangles, you can do these things called Taylor models, which are able to represent more expressive sets. We don't have to deal with these hyperrectangles anymore, so we're going to get better. I don't know. Yeah, I think we'll stop there today, but maybe here's a preview of what's coming next. So exciting. Oh my gosh, look how much better it is. Look at this bound here. Like, whoa. Okay, so if you want to know how to do that, you should come back next week. And tell your friends. Okay, have a good weekend, everyone.